So now let's do an example. So we're going to use the CSTR mole balance to solve a reactor design problem. So the example, a liquid phase reaction 2A goes to B is being carried out isothermally in a CSTR. The rate law is K times the concentration of A squared. The rate constant K is equal to 0.03 liters per mole per second. Species A is fed to the CSTR at a concentration of 2 molar and a flow rate of 3 liters per second, and species A exits the reactor at a concentration of 0.1 molar. So we need to determine the rate of reaction in the CSTR as well as the volume of the CSTR. So we can do this by using this mole balance. First, let's determine, though, the rate of the reaction. So the rate of reaction, so RA. So A is a reactant, which means in this reaction it's going to be net consumed. So the rate of A, the net rate of A, is going to be negative. And we're given an expression for what that rate is. It's K times CA squared, where we know what K is. So what this says is the rate of A is negative. So the concentration of A is decreasing over the course of the reaction. A is net consumed. So let's write this in. So RA is equal to, what was that, 0.03 liters per mole per second times CA squared. So what value of CA do I use here? I have two concentrations in my problem statement. I have this 2 molar, where the A is fed at a concentration of 2 molar and it exits at a concentration of 0.1 molar. So what is the reaction rate then inside the CSTR? Which one of those values do I use? So as we talked about in the last part of this lecture, the CSTR operates at the exit conditions. So that means the concentration inside the CSTR is the same as the concentration of that exiting the CSTR. So the rate in the CSTR is going to use the exit concentration. So if I do this math out, I get that, and then this should be a negative sign here. RA is equal to negative 0.0003, and then the units on that would be moles per liter per second. So moles per volume per time. And check my math on that, because I could have done it wrong. So now for the volume of the CSTR. So we're going to get that from the CSTR mole balance, and we already know what the CSTR mole balance is. We just derived it. So because of that, I'm not going to derive it again, and you don't have to derive it every single time on a problem statement either. If you want to, you can just write it down. So that's what I'm going to do. V is equal to FA naught minus FA divided by minus RA, where minus RA is equal to KCA squared. Now, there's one issue here. On the top here, we have flow rates, and these are in units of moles per second. These are molar flow rates. On the bottom, we have concentration, which is in terms that are in units of moles per liter. So basically, these things are describing the same thing, which is the quantity of A being fed versus the quantity of A exiting the reactor. But they aren't in the same units. And we need to put them in the same units in order to be able to solve this problem. So we're going to use the relationship that between concentration and flow rate. So concentration is equal to molar flow rate divided by volumetric flow rate. So this script V, not to be confused with the nu that we saw with stoichiometric coefficient, the script V stands for volumetric flow rate. And it just so happens that in the problem statement we are given this value, flow rate of 3 liters per second. So that's the volumetric flow rate. So we can fill that value in. So what we've done here is said that the inlet molar flow rate, FA naught, is equal to the volumetric flow rate times the inlet concentration. And same for the flow rate coming out. The molar flow rate of A exiting the reactor is equal to the volumetric flow rate times the concentration that's exiting the reactor. So if we multiply those things together, this is in moles per liter, this is in liters per second, so that gives moles per second. So it works out. So this is now something that we can solve. So V is equal to volumetric flow rate, 3 liters per second, times our concentration difference. So we had 2 moles per liter minus 0.1 moles per liter, times our reaction rate, which we know from above. Our reaction rate is equal to minus 0.0003 moles per liter per second. That means the negative value of that is going to be positive. So I get, if I solve that, I get that V is equal to 19,000 liters. So if I divide that by 4, that would be approximately what the volume would have to be in gallons.